Okay, so your lab is due tomorrow. Does anybody have any questions on it at this point? I think most of the groups that had questions are here and seem to have solved them.
Due tomorrow or Thursday?
Tomorrow is Wednesday, being Thursday. Thursday before class. Yeah. So I've now given you guys your daily, your heart is still working check. Yep. Okay, so you don't have questions now. Forever hold your peace. So the other thing, I wanted to mention this. Dr. Nenny is going to be posting your blogs on semi-weekly sequentially over the next week. We have our first post already. Tanner, Adams, and Christian's post is already on, and we have a little blurb on there about you guys are writing about a contemporary issue, and we are getting good comments. The reason why he's posting them is because when he posts them, it goes on the front page. If you were posting, it would just go on one of the side ones. So you guys are getting maximum exposure. So you have people coming in and mentioning their comments and particular. Now here's an interesting thing. So if you want to go once you've logged in, since you all have an account, you can go in. You can actually send him a private message or respond to his comment. I highly recommend this. You have basic information, the information they've chosen to disclose. This guy's the editor-in-chief of EE Times Asia. He's also wrote 6 books on the Internet of Things, smartphones, Nokia smartphones. So for this group, you guys have a pretty good connection. So you now have 5 connections. I encourage. That's a wink. Not just because it'll be a good thing for you to have on your presentation at the end of the semester, but think of it this way. Your group has 5 connections that no other electrical engineering or computer engineering person in the world right now has. All these people you're going against, no idea who these people are. So you have a leg up. So absolutely take advantage of this opportunity. Daniel Payne is on there. So he's posted a blog for you guys to take a look at. So basically, cycling semiconductors and CES. So at CES, they were Strava. They do an app. They're trying to keep track of distance and calories. And so basically what they've done is they've connected a chip to the pedal, and they use energy harvesting to actually power the chip. So the actual process of moving your foot powers the chip. That actually, typically you use an inductor to create a difference of potential, and that difference of potential can then be used to create all your channels that are required to power the CMOS chip. So you can make an allusion to this and say, well, we spoke with, one of the people we spoke to is Daniel Payne, and you can go on there and talk to him. This guy, he had a little advice about blogging, but unfortunately it was we kind of went with what Dr. Nenny said. He says, but I did read it. I think environmental scavenging of power is going to be very important, as well as the devices. So, and then Chip Guy here, he thinks that you guys wrote a pretty great article. And the Internet of Things, and he's adding smiley faces because he doesn't, what is exactly the Internet of Things. If you're trying to define something, you have to use the word things. It might be ambiguous. But then he kind of goes on this whole spiel about, what you guys were blogging about. So you can kind of take, his questions and thoughts, and there remains lots of questions about how this can be applied. What are those questions? Reach out to all of these people, create these connections, and if they are on here and they know lots of people, they can put you in contact with other people. Ultimately, educate yourself, learn things that you normally wouldn't learn in class, potentially get a job if you hit the right connection. So the worst thing you can do is you can just cast out a lot of, So anyway, congratulations to your group. You guys are the first one posted. All of you you can actually refer to this as, on your resume. Say we've been published on SemiWiki. Here it is, right there. Include the link. So, especially since if you're for those of you who are starting to apply for jobs, you see writing as a skill is often, they want you to show that you're a good writer. And usually the only thing that they have to refer to is your resume. So you have you can competently describe yourself, which you're never going to do once you actually get hired. You say, hey, I've read something that was outside the scope of the class. I described it technically and presented it to professionals, and it went well. Here you go. Here's proof that no one else has. So you guys I would highly recommend taking advantage of that in the job application process. So let me go to today's lecture. So for the next two lectures, I'm going to cover rule checking, adders, and the data path. This is going to basically cover many of the things that you'll need to know in order to complete your Lab 2, which is still due next Tuesday. If your heart's pumping, okay, whatever, that's when it's due. And so we're going to be going over this concept of design rule checking and error rule checking. We're going to briefly go over full adders because you're actually going to take a schematic of a full adder and render it in the electric VLSI designer. And then you're going to take the data path and control of the MIPS data path. You're going to manipulate some Verilog. You're going to add one instruction to the control finite state machine, and then put it in there and make it work. So we're going to discuss that data path and how it works. Does anybody have any questions before I go on? Right. So there are two types of analysis and we're going to apply this concept of rule checking to. The first one is called static analysis. The whole idea of static analysis is you just have your chip there, and you're making sure that it meets all the design rules. You're not putting anything into it. You're not putting any waveforms into it. You see if it physically lays out properly. Whereas dynamic analysis is when you're actually putting in inputs and checking to see if the inputs produce the correct output. So static analysis formally examines a circuit that's devoid of input and data, and therefore it does not change over time. And dynamic analysis examines an energized, time-functioning circuit. So you have a number of restrictions. We're actually going to be going over some small examples of the MOSIS DRC, which is the industry standard, which applies like metal 3, metal 4, all these different layers, and how it's scalable. It's called Scalable CMOS or SCMOS to the lambda-based design rules that we've learned already in class. So the lambda-based design rules were the SPICE level 1, how that is applied to our design rule check for everything we've done so far in class. And we're going to then see how we scale down, because we have to maintain the ability to make chips as we're reducing the technology size. So in order to do this, we use design rules checking. It's concerned with the physical placement of the CMOS layout. So that's why static analysis is more appropriate than a dynamic analysis, because dynamic analysis, you've done this, you did this in 385, you've done this in any other class where you've put in inputs and read the outputs on the output, right? That's dynamic analysis. How did things change? Dynamic analysis is an example would be your D algorithm. Put in a set of inputs. Can we actually determine whether or not we can actually read the error, right? So we're also going to be using electrical rule checking, which checks the properties of the circuit that can be determined from the geometry and connectivity without understanding the behavior. So for example, we discussed the geometry of wires, and we discussed the geometry from the stick diagram. We discussed applying the lambda-based rules to be able to design an inverter. And in this next lab, you're going to be doing this with a NAND gate. And so basically everything's based off the poly and the N well, and you have your pins and the P well, and everything has to be certain distances from each other. And now we know more why. We understand that there's capacitances when you have two different plates. And you want to make sure that you reduce that amount of capacitance, because you want to reduce the logical effort of the device. So in order to do that, you have to meet these certain electrical rule checks. And then last thing, in order to do, you want to be able to perform functional, some sort of verification. So there's two different types of verification that we've discussed. we're just formally defining what I hope at this point is now intuitive: functional verification and timing verification. The functional verification, does it do the exact function you want it to do? Timing verification is, does it meet certain timing constraints and performance constraints? So formally, formal verification: operation of parts is aggregated into an overall function for the circuit. So what we're going to be doing, we're going to actually be discussing how we're taking this different geometry layout and seeing if it actually performs some sort of functional function that we want to do. And then timing verification: the delay of the parts is aggregated into an overall speed of the circuit. So we've done a number of problems in previous sections where we've been able to calculate these types of delays. So I'm moving this chair. Grad student. Okay, so we're going to be, in order to do static analysis, there's going to be some different stages and different approaches we can do, because there's pros and cons. So for static analysis, we need to actually take this geometric layout and kind of scan it through in order to see if it actually, meets it. So if we just have a, I can just draw here. So we have some polygons, and we have an end well, right? We discussed before, and then we know that these have to be a certain length apart, and we know this has to be a certain size, and we don't. But if we, let's say we're scanning this, and we scan here, so we have a block that we're moving it across, and this is what's known as raster-based node extraction. So we have a grid of points, and we're scanning and scanning. So basically, every time we come across something new, we're creating a new node, and our new node is going to represent our new circuit element. And based on that circuit element, we're going to be relating it back to a certain amount of area, and that based on that area, we can then determine if all of these rules are being met as we scan through the circuit. So let me get rid of that. So then we have two that we're going to discuss here. Oh, so for such thing, node extraction. So nodes, we're going through the circuit, we're grabbing these polygons, and we're creating nodes, like a graph. So node extraction is the process of converting a finished layout from pure geometry to connected circuitry. We're checking to see how these actually connect and how this, the flow of the current and how the voltage and how our sizing impacts the ability to reach our noise margins, our timing of the circuit, design constraints, etc. Then the two that we're going to discuss: polygon-based node extraction uses the complex geometry that is produced by the designer. So you now have a design rules check that MOSIS has it in there, so it scales. It's Scalable CMOS. And then you use your device model that has the specific technology file that you're going to. So it has to meet these specific DRC complex geometries. And there, it's going to use the device physics that have been calculated in your model to be able to see if it actually physically meets these requirements. So that's how we're doing this static analysis. All of these things are combined together into the tool. And 8.8, raster-based node extraction, which I kind of alluded to, we'll go over an example here in a little bit, reduces everything to a fine grid of points that is simple to analyze. And here's what I mean by that. So this is an example of raster-based node extraction. So we have a simple transistor, and the black window here is used to scan the contents of the, quote, raster image. So what it's actually what the tool is scanning is this portion here, and it's going to be moving. And this is actually the description of the movement. So the lower right corner here is guaranteed to always be positioned over something new. And so what it's doing is so we have some sort of poly, and we have an end well, right? So it's moving, and the first thing it's going to do is it's going to see the poly, and it's going to register the poly as a node. And then eventually it's going to move across and move across and move across, and it's eventually going to say, oh, hey, I'm hitting an end well. So we have certain width that the poly has to be. So when as it moves up, it's going to say, oh, hey, this node is now 1, it's now 2, it's met the design constraint. If it was 1 and then it moved up and there's no poly, it would throw a DRC error. Similarly, if these aren't allowed to overlap or we haven't connected them properly, we'd be able to detect that by moving along. So you have to constantly relate it to the previous data that you have. You're collecting a database of the circuit as you're moving along, and as you're moving along, you're starting to connect them. So before, you just have a bunch of polygons that you've laid on top of one another. And as the raster window moves across, you're actually connecting the circuits together in order to actually, physically determine how the circuit works and perform your static analysis. Okay. Does this make sense? Okay, good. So this one is just, we're going over the grids of the circuit. Polygon-based node extraction actually physically finds the polygons and compares the polygon to their adjacency to other polygons. So it's different. So here think of it just raster just scans everything. It's real simple. Polygon finds the polygon and then seeks around the polygon to see, and the design rules will control how far away you look for a certain thing. So let's say you guys are our circuit, right? And I am the design rule algorithm. So Tanner here has a certain amount of distance he has to be away from another student. So let's say that distance is 2 rows. So that's 2 lambda. So this circuit hasn't been well designed. So I'm going to come in. So the first thing I come to Tanner and I say, all right, he needs to be 2 rows away from another student. I check. I see that Christian's here within 1 DRC error. Right? But let's say that I'm so sorry. I apologize. I've only seen you 1,000 times, and I'm so tired. Tyler. Okay, so Tyler's a different set of rules, and this is what happens when you've been up since 5 a.m. in the morning and you forget names. So Tyler's a different set of rules. He's allowed to be within 1 of any student with a beard, right? So I check around. Yeah, he's fine. Yeah, he's fine. Yeah, he's fine. Okay, good. He meets all the rules, right? But now, your specific rule, I'd have to move you. I'd either have to move everybody over 1 in order to make that work, or do something else. So that's polygon-based abstraction. That's based on the size and based on the type, right?
In designing like that, do you start with the smallest and work your way out to the biggest?
No, it helps to transfer. This should answer your question right here. They try to transform the polygons before analysis in one system, and there's different approaches. But in one system, all polygons are converted to strips about horizontal lines. So it's kind of slightly trying to merge the polygons into a kind of raster-based analysis, but instead of reading every single one, they're like, all right, this polygon has 5 across this way, is 5 lambda across, 5 lambda across, and so forth. So it's not really based on size. So the last thing we're going to talk of the 3 major ones, we're going to talk about this concept of network consistency checking. So when you start laying out a network, it's useful to know whether the desired circuit actually matches the topology that you want it to have. And what I mean by topology, and I'm going to kind of give a quick preview to the next figure, right? So here, these are 2 logically equivalent circuits, right? We have a NAND gate and an inverter, and there's feedback from the inverter to the second input of the NAND gate. So we do a .IC command to initialize the voltage to 0 and then be able to simulate the circuit. But these have different layout topologies. This one flows right to left, kind of intuitively how you draw it out. This one is a little weirder, because at some point, you have a really long wire. here they're making this wire short and then bringing it out here. So you have wires crossing, so you have to worry about the levels, and you also have to worry about, but you also have to trade off in width. So here you have, in order to do feedback like this, here the moment it comes out, it's there, but it's, you consume less power. But if you do a different width and you cross the wires, then you're able to have it on the output. But here's the thing. Network consistency checking will make sure that these are functionally equivalent, meaning that it's going to start at the AND gate and say, all right, well, I have one input, right? It's going to create it like a graph. And how many of you are familiar with graph isomorphism? No? All right. The whole idea of graph isomorphism is it compares two seemingly looking different graphs and sees if they are actually, in fact, the same graph. So, for example, if I have A, B, C, and D, right? And I have a box. And then I have A, B, C, and D. Those two graphs look different, right? And if I were to connect B and C, I mean A and C, and these two graphs are functionally equivalent. Right? So in order to do this, we have to start at this node and say, where do my edges go? And then we check the next node, and then there we can have the edges in those graphs, and we go to each node and see where the edges go to. We compare them. And what we would find is that all the edges go to the same nodes, and all the nodes have the same edges in the graph. And therefore, they are functionally equivalent. So that's graph isomorphism. So what we would be doing is we'd be going to some sort of node here. In this case, it's a NAND gate. We've created our node. We have one input edge, and then we see this AND gate again as the same input edge. Then we have another node B, which is an inverter. That edge comes from A. Here, C and D. See how this edge comes from D? So it turns out these are functionally equivalent. So you have to compare equivalency. You have to compare functional verification. You have to make sure that the circuit meets your DRC, and you have to make sure it meets your electric rules check. So all of these are, come together, and what you want to do is, let's say, for whatever reason, this circuit didn't meet your geometry. It passed the raster, it failed the raster-based node extraction. If you move it down here, maybe it meets your layout. It meets your DRC. It matches if the layout geometry works, and it's functionally equivalent. So we'll check your functional equivalency. Yeah, equivalency rules check, and then it'll actually make sure that the circuit actually works. Does that all make sense? So let me quickly formally define network consistency checking as taking a schematic and layout geometry and compares the two networks by associating the individual components and connections. So as the circuit gets larger and larger, it becomes a much more impossible task. So what you want to do is you want to break it down into nodes. Remember in the last section we were talking about branching? And we're trying to reduce it by breaking it down into cells. So what you want to do is you want to try to have this NCC, the network consistency checking, try to have as high up in your branching tree as possible. So if you're trying to compare a bunch of smaller cells, ultimately it's not going to work, right? Because imagine how complex it is just walking through two nodes and 3 wires. But if you're trying to do millions of transistors, it can become problematic very quickly. So you try to reduce the scope, make sure it's checked, and then have these larger registers, register transfer language. ALU comes from adders. Adders come from XOR gates and NAND gates and OR gates. So you're trying to reduce the scope, and that's why your CASCI chart is so important, because it allows you to reduce the complexity of your checking. Yes, Tanner?
You're saying reduce the scope, but how much should you reduce the scope? Like,
Well, that's where different coding level works. This is actually a very important question. So the question is, how much should you reduce the scope? So you have, SPICE, right? SPICE, the scope is on transistors. Make sure your transistor size works. So we've also done Verilog and VHDL in other courses, right? So VHDL, you can do gates and do registers. And then you can use the architectures that you design in Verilog and VHDL to then test it at even a higher level. So you have to focus on different levels of abstraction. And this is why computer architecture is so important. System attributes of a computer that contribute to its logical execution and are visible to the program, right? So you have these system attributes. First, you have transistors. You have to make sure it physically works, right? So that's SPICE, all of this that you're learning in CMOS. So then CMOS, you then design either registers or PLAs, anything that works you can work in an embedded system or an application-specific chip or a printed circuit board. From there, you actually want to use Verilog and VHDL to formally verify your architecture level, meaning everything that you're using to build up to the RTL. So it's not possible to check every chip, then check every single wired circuit, and then check everything by yourself. The whole team is going to be working on that. So your architecture level, your VHDL and Verilog people are dependent upon the CMOS people having properly verified it, right? So those building blocks are then going to be used to build that. So from VHDL and Verilog level, then you're going to be trying to make sure that your circuit is properly formatted, so you can use C or System C or C++ to be able to design that. So that way your instruction set architecture, which we'll cover a little later, properly matches the physical level. So remember, you have compilers. Your compiler design, YAC, GNU, you're going to be able to compile the C down to the architecture level. And then if you want to deal with the operating system, let's say you want to disassociate the architecture with your OS, and this becomes important because you want to take your operating system and be able to have it work with any architecture. That's when you use the Java virtual machine. So all of these different levels of abstraction become important in the design of a good computer. I probably answered your question a lot more than you. But does that make sense?
Yeah.
Okay, good. So good, I can formally define graph isomorphism as equivalence relation on graphs such that it partitions all the class of all graphs into equivalence classes. So you're going to be taking different, so in the graphs that I drew up there, all of the nodes are the same. But when you do a CMOS circuit, because I'm following up on your question, when you're doing NENWEL or PWEL or poly or metal 1 or metal 2 or vias, they're all different types of nodes, and they all have different types of edges. So when you're going through the graph, you're going to be checking to see, is the node type, the inputs, the outputs, and the nodes that's connected to. And based on that, you can then see if the circuit, if the edge is the proper distance away, then you can check to make sure if your circuit works. Then you can it allows you to reduce the complexity of checking through it. So the reason I'm kind of getting back to your question, Terrence, is because if by reducing the complexity by going along the graph, you can actually check locally to make sure if the circuit works without having to worry about the overall functionality of the circuit. So you can disassociate your node extraction and your DRC from your functional verification. Okay, so then I kind of added here for those of you who are kind of interested in how things are working in data structure level. For graph, I film over using a hashing function, hash tables, and combining the components into integer. And each component is addressed by a single integer. So you have an integer type. So it's the type inputs and outputs, edges. So then you can kind of go through, using the hashing function allows you to quickly read through the circuit. So by using that, you can reduce the overhead that this has compared to Raster base node extraction. Okay, so I want to kind of go over an algorithm here. We're going to go over a simple problem here in a second on polygon-based design rule checking. So we're going to take this concept we just talked about and actually see what is actually done. So the earliest attempts for design rule checking, we're going to have well, it's technically 6, but 3 of them are essentially the same. The earliest attempts at design rule checking were based on algebra of polygons. So you're trying to see how the polygons actually add together or not. And then you use the design rules to see, kind of here this error, see if you can actually find an error, and we'll discuss this in a second. So the first one, merge, combines overlapping polygons on the same layer into one that contains the union of their areas. So in this, I'm going to scroll down. So we have both of these. So first thing, let me define bloat too, because that'll make this whole drawing make more sense. Bloat expands the polygons on a layer by a specified distance from their center. So here we actually have a bloat. You see they have the original size, and then you have a specified distance from their center. That's your lambda-based design rules. No signal. Yay, all right. So use the lambda-based design rules to bloat out the size of your circuit, and then you have some sort of overlap, right? So then you're going to use merge to bring these all up to the same level, right? So before they're on different levels because you want to maintain different levels of abstraction. Then you merge them together onto the same level. And then using that bloat, the bloat is you've created a polygon, and then the bloat is the area around the polygon, which, something else, this poly 1 and poly 2 are not allowed to overlap. So this is the particular problem. So the other functions and, or, and XOR are interlayer operations that find the intersection, union, and exclusive areas of 2 different layers and produce resulting polygons on a third layer. And then the last one is touch, which finds all polygons on one layer that adjoin or intersect polygons on another layer. So what we've done in this figure below is we've used bloat and merge and as an example of finding an error, right? So we have poly 1 and poly 2. And then they have some sort of, in this case, it's some sort of, they're both bloated by 1/2 of the minimum spacing. So that is our bloat. By having that bloat occur, we can now check to see if these overlap at all. We have a problem. So if they overlap at all, the error is found using by the and of those two, the union, right? So here in the middle of B, we actually see that there's a small overlap. You can't. So those of you who can't see in the back, let me zoom in. So here we have our small overlap. So then what happens is we merge the layers together. We take the and, meaning we're taking the union, which becomes this portion, and that becomes our actual error. Does that make sense what I've just done? I'm going to walk through it again. Okay, so I've kind of made a little working note. If you're trying to do a whole circuit of this, the problem is that as the number of polygons get bigger and bigger, it requires much more space. So one says they try. We recommend running it incrementally, trying to focus on different subsets of the entire circuit. And we're going to discuss this in a moment, called the working set polygon comparison. So instead of trying to do all of them at once, what it's going to do is it's going to kind of do a hybrid version of polygon and raster, where it's going to go through, find a small working set, check that, and then once that's done, I can move on to the next one because I've guaranteed that this circuit won't work and there won't be any contributing contributing errors to that particular portion of the circuit. And then I can say, well, I don't need to hold on to that anymore, it's fine. Then I check the next working set, and then I check the next working set, and check the next working set. So it's kind of a hybrid of the two approaches. And so we'll formally define 8.12, the working set polygon comparison, as comparing neighboring polygons and sorts the edges along one axis. So we said earlier that it's most commonly horizontally, and it's for no other reason than most people like design from left to right because we read from left to right, or from right to left in certain countries. Not to discriminate, but that's kind of just it's intuitive. It makes sense. So here we have a set of circuits. So here, this black line is our scanner. So it's actually going to be coming through, and it's going to be comparing the different polygons. We have a circuit, and the purple in the different in the circuit. So this is three representations of the circuit, and the purple are the polygons that are touched by the scanner. So the scanner determines the working set by saying, well, I'm here and I'm scanning from left to right. This means that this polygon here, this polygon here, this polygon here, and this polygon here are the ones that I'm currently comparing for my design rules. And then I move again. If I move over, I hit a vertical edge. Suddenly, this polygon joins the set. Now once I move here a little more to the right, that means this polygon here in the middle, we've now moved past that, so it's no longer part of the set, so it's out. So we're just checking the DRC of the specific ones that are being touched. I've already said all of those things. Okay, so does that make sense how the working set polygon works? Okay. Tyler, now that I'm remembering your name. Thomas, Christian, Terrence, Jason, Tanner. I remember everyone's name now.
The T's have it.
Yep. Right. Okay, so I've already described all of that. Okay, so hierarchical design rule checking. So I've stressed the importance before in this semester about maintaining different levels of extraction. And that problem that I told you about where people get, frustrated and they spend hours and hours checking. Here's what happens. We have designed our cells. We've designed an XOR cell. We've designed an OR gate, right? So in the process of designing the XOR gate, we short out one of the inputs. So basically what we have is that we have an input metal 1, and then somehow in the process of the design, we have inadvertently connected metal 1 to ground. So it shorts out and it passes DRC. So it's past our design rule checks, it's past our static timing analysis, and it gets all the way up. So then what happens is merge, bloat, and or XOR, touch, everything works. And in the process, they then do this thing called flattening the circuit before checking it. So they get excited, oh, hey, past DRC, woohoo, I'm flattening the circuit. If you maintain hierarchical design rule checking, what happens is if you get an instance where you're getting wrong outputs, you can then go back to the cells and check there to see what happened. Okay, well, the first thing I'm going to do before I do anything else, I'm going to do my troubleshooting like we did before. Then I get down to the fact I see that clearly my XOR are just producing the outputs. and then I go to that cell. So instead of flattening it, I look around and see what I've done. Oh, hey, my E input is shorted ground. I fix that, check the DRC of the XOR gate, and then I can then check the DRC of the full adder. So if you don't do that, you just flatten it without using design principles, then you go in here, you take this out, and as the circuit gets bigger and bigger, and if you flatten the whole thing, you not worry about cells anymore, and you have 12 XOR gates, or 10 AND gates that aren't working, or wires are screwed up in the wrong size, suddenly you run DRC and you have 100 errors, and you lose your mind, like, what happened? Well, it's only really one error. I always maintain the hierarchical design rule checking. I maintain that until you've tested everything in a particular circuit that could possibly happen. You've done all of your DRC, you've done all of your electrical rules checking, you've checked any network equivalency checking, you've done all of your timing constraints and functional verification. Once you've done all of that, then you may flatten the circuit. So next thing I want to do is I want to cover some electrical rules. We've talked about geometrical designs. Here's the important line in this little write-up I've written. Everything we've done up to this point today in class has not proven that the circuit will actually work. All we've done is that physics are okay. Right? We have not violated any physical laws. We've not violated any fabrication or synthesis laws. Everything is okay on the DRC end. But now, we need to see if it will actually meet our timing constraint analysis. So we have to determine the geometry, how the geometry and connectivity of the circuit work together. And we have to do this before we actually go and do the functional testing. So, for example, the estimated power consumption of a circuit can be determined by evaluating the requirements of each device. So here we have two circuits. We have Phi1 and Phi1 bar, and here we have Phi2 and Phi2 bar. So these are two implementations of the same circuits. So we have two pull-ups that will not be active at the same time, and therefore can be estimated to use the power using only one pull-up. So if you basically what all this means is recall when we were putting together static CMOS and domino logic. And we want to check to see if our domino-based logic actually works. So what we do is we need separate phi values or testing values to be able to see if the circuit will actually work. And therefore, in order to do this, we need to test our PMOS and NMOS using inverted values. So phi and phi bar, phi and phi bar, PMOS and NMOS. They should be the opposite. And that's beneficial because there's going to be that instance if we don't test if we make it go too fast from section 7, we get that spike. Yep. So by having the appropriate rise and fall time in our electrical rules checking, we can then see if physically we pass a signal in and we get a reasonable signal out. And so that's different than the correct signal. You have to test whether the signal appropriately works for all possible input combinations and works with a certain rise and fall time. So let me see. There's 3 stages. So you have DRC. Is the layout proper? ERC. When I put in the appropriate signals, the circuit operates in an appropriate manner. And then your functional verification is, does it actually do the logical value that I want it to do? And then once you do that, then you can have it work as a cell, and then you can pass it over to your VHDL designers who then do your architectures and so forth. So here, this is kind of so you have some sort of input, and then recall we have our gate tied to the output, and then that drives the next NMOS, and then we have our output tied to the gate and our drain. And so we can use this in coupling considerations. So basically, we can use the ERC rules to test to see we have one input, right? Will this drive the first inverter, and then will it drive the next inverter? And then you can test to see if it, and the important detail here is you want to focus on frequency and power consumption. When it's going at a certain speed, how will it operate? If I double a speed, if I put it as 1 gigahertz instead of 100 megahertz, what will happen? You can test noise margins. This is a good thing you want to do in the ERC checker. Will it actually meet my noise margins? When won't it meet my noise margins? So I know that if I have this circuit, and I know that that at 900 megahertz it fails my noise margin checks, then I either need to resize the circuit or say this is a cell that can be used for 900 megahertz and below. But the moment you put this into a 901 megahertz circuit, it will fail noise margin checks, it'll fail ERC. And so a lot of that power estimation, as we now know in this course, relies a lot to do with capacitance, load capacitance times VDD squared times frequency. And so we can use all of this and to do all of these kind of electrical rules checkers. And the last thing I want to, before I go on to transistor ratio checking, does everybody understand what I've been talking about so far for this? All right, so transistor ratio checker, I hope at this point you understand what do you think the goal is? Don't read the word for word definition, just intuitive. What do you think of transistor ratio? I really hope you guys get this right. I'm not going to call on Tyler because I already got his name wrong today, so I feel bad. But transistor ratio checker, other than it checks the transistor ratios. What types of transistors? What does the C in CMOS stand for? And what is the complementary? What is
It's like NMOS.
Yeah. See? You guys are like, oh, come on, this is the first day of class now. You guys, yeah. Complement. So basically, now we're just going to be going through, and let me read this out formally. Transistor ratio checker determines whether the appropriate relative scales or ratios of the driving components are met to achieve proper logic transition. So we know what that means now. We've discussed this. We have an instance where either we raise or lower it too high, or we don't have a properly ratioed circuit, so our rise time and fall times don't meet properly. And so we use this transistor ratio checker to basically do all the math that you guys have done in the previous sections 4, 5, and 6. So if you have a NMOS transistor that's 1 and the width and length are the same, and then you have a PMOS transistor that has 20, your transistor ratio checker is going to throw a fit, right? Because one, your NMOS transistor is not going to be sufficient to properly draw the current, and then your PMOS transistor is going to draw a huge source of power because its width is 20. So you want to actually take advantage of these transistor rule checkers in order to do this. So here is our example. We have our 2 to 1, and then it's so this becomes 2 and 4, right? And then this becomes 8 and 2, right? So that's how we designed it before. Here we have a circuit where, like just what I talked about, instead of having it 2 to 1, it's just the pull down ratio is 1 to 1, and that becomes problematic, right? And this is an inverter circuit. I should emphasize this is an inverter. So our transistor ratio checker would catch this. And I kind of added here at the bottom, we can use op-range function in SPICE to try to figure out what the optimal circuit should be for the particular frequency we're running, for the particular model that we're running, and so forth. So, does this make sense? This is an example of what would be caught by this. All right, so in this course, you've already learned an example of a DRC. So remember these 6 rules from back in section 1? These are the fundamental lambda-based design rules. And so everything that's been built on this has these rules as a fundamental. Now, if a specific company is doing a specific do their own foundry, they're going to have their own design rules that meet their specific implementation technology. However, in order to maintain proper scaling, if you want to try to do different technologies and try to figure out, do I want in 0.18 micron, do I want in 0.13 micron, do I want in 90 nanometers? You can use the different, you can use a .include and use your different technology file, which those of you who've done the lab, you've all used the AMIOS6N and .m file to be able to do that already, to render your IV curves. All of that's based on this, the physics of this. So if you want to be able to have it, if you want it to be scalable, meaning you have some sort of, you have some sort of value in the SPICE deck where you're saying, all right, I want it to scale based on this technology, then you can use what's known as Scalable CMOS, and the industry leader is known as MOSIS. And MOSIS, especially if you go to the Design Automation Conference, you'll become very familiar with MOSIS. Anytime they work a lot with industries that don't have their own fabrication labs, they work with academics. So if we decided we wanted to make our own chip, and it's not funded, we can send it off and they fabricate it for us. And these people have become very important. Dr. Nenny runs SemiWiki. Has a lot to do with MOSIS. He wrote that Fabless, the Fabless book. Fabless, you use these tools to design a chip, and then you send it off to a fabrication lab. And so MOSIS is Scalable CMOS, takes these lambda design rules, and uses a set of logical layers together with their design rules, which provide a nearly process and metric independent interface to many CMOS fabrications. So the whole goal is use your lambda design rules, then you put it in, and then based on the technology that you're using to meet specific power and size constraints, you should be able to scale it down to different technologies. Remember that graph I showed you with the size of transistors going down through similar to Moore's law, and then the number of transistors per chip is going up. So you want it to be scalable, and we have issues that happen. The chip becomes smaller but consumes more power. So you can use this MOSIS tool, MOSIS company, use Scalable CMOS to do that. Now, Intel, I remember this diagram I showed you back in section 4, where here we have 5 metal layers, and here's 8 metal layers, more compact. When you have to use them to worry about, different directions, and we, trying to maintain the distances now that we have to worry about Miller coupling factors. MOSIS tries to use the same technology scale for pretty much, all you do is change your .include file and make it work. So that's called Scalable CMOS, SCMOS. And if you wanted to, when you're done with your lab, you could actually send off your final chip and have it fabricated, if you like, through MOSIS. And so here, this PDF, it actually has the industry standard design rules check, the DRC. We're going to be going over some kind of fundamentals, like just 3 different sets of them. The first one are the well rules here. So you have minimum width and minimum spacing between wells of different potentials or the same potential or between different types. So 1.1 is just the width. This is the minimum width of the N well. 1.2 is the different potential. See the N well and P well are connected, so they have different potentials. So this is the minimum width. And these are the actual lambdas that are used. 1.3, and for now I just want you to worry about these. We're not going to, this is a sub-micron and deep micron are a little outside the scope of the course. And then if they're different type, the minimum space is 1.4. So here they actually define it as 0. So now let's say they're active. So we have some active wells within our P well and N well. So we have our minimum width, 2.1. 2.2 is the minimum spacing between two active areas. And then 2.3 is your source to drain well edge. So here you have two active wells. I'm sorry, you have P region and N region, 2.3. You have N region and well region right here. So that's 5 lambda or 6 lambda. Oh, I'm sorry, that's 5 lambda here. So 5 lambda, 5 lambda. 2.4 is substrate well contacted. So here you have an active and you have your P substrate. And that's 3, so that's different than 5. So you can see the sizing there, sizing difference. And the minimum space between your of a different implant. So here you have actives and actives here. So here you have Pn plus, here you have P N minus and P plus. So here you have the minimum distance between two actives in two different types of implanting. So that's the different sizes there. So all of those, so basically let's say you're going through and you're using polygon-based design rule checking. Here what you're going to do is you're going to use your scanner to do it horizontally, so the scanner goes vertical. Here we initially do N well, P well. We hit these two actives. They're just going to check the distance, rule 2.3. It's fine. It's going to check the widths. It meets the minimum. It's going to keep going. It's going to keep going. It's done. So it's checked the width on both sides. So then it's going to see, for 2.2, it's going to say, I shouldn't hit another one until here. So it hits here, it works fine. Continues, we check the exact same thing. We go here, we go here, we go here. We hit this new dopant. And so the check's going to say, hey, I have a different distance, in this case 2.5 of 4 lambda, before I should hit another active. So once it gets here, it's then going to say, well, I've hit 2 actives in 2 different types. Have I met my distance? So it's going to check these distances here, and it's going to see that it's met, and then it's going to check the minimum area, and then eventually it just gets this piece and select. So that's how this all works. Now, if it was raster-based, it would actually start here, and it would start collecting the nodes and move along, and then eventually it would hit locally enough to actually check all of the rules. And then for poly, so this is the last one for the layouts. For the poly, we have our minimum width, which is 3.1. So we all know that's 2 lambdas. So our scalable CMOS has matched what we've learned in class. Everything here for minimum space over field and space over active. So 3.2 is over the field, meaning it's not over an active, right? So this is just polys connecting to portions of the circuit. So when it's over active, it has a minimum spacing. It's the same. It's 2 lambda here. 3.3, the minimum gate extension of active. So remember when we were doing our stick diagrams, right? And I had VDD and ground, and I had P well and N well, right? And we were drawing out the poly, and I was insistent on having this little overlap here, right? The reason why that is because of this rule here, 3.3. You have to have a 2 lambda overlap. So you have an active, these are active areas. So you have some sort of active pin in the well, and then you're going to have 2 lambda over the active in order for it to work. So that's why I was so insistent at the beginning of the semester that you should do that. And then 3-point fel, let's say you're running a poly along the active, you have to have it has to be at least lambda 1 away from an active as you're moving it, in parallel. Right? So you go over, let's say I did it this way. Let me do this. So we have our poly. Here's a common mistake people will make. They have their poly here, and then what they're going to do is they'll do another poly, and they run it here, right? It's going to pass this DRC, but eventually it's going to hit this, right? Actually, that should pass. Yeah, that'll pass. Okay, let me find a better example. Here we go. I do that, right? What's gonna happen is it's gonna bloat, it's gonna merge, it's gonna do an and it's gonna see that I have an over, so it bloats this over, and it bloats that over, and the area will be thrown by your DRC. And the typical design rules checker, when that happens, the area that it'll have a giant, the area that occurs, it'll have a giant flashing X. And you go, okay, well that's where, and it'll have some number, and then you use the, you can go back to your PDF and it'll say, what's the number? You check it back there, oh, I violated this rule, and go for it. So these are the, I should also emphasize, these CMOS layout design rules are the ones that are used in electric VLSI designer. So that's why I'm presenting them here. They're used industry-wide, but they are specifically used for your class, too. Okay, so another thing that you're going to be doing in the labs are full adders. So this is kind of a basic review. I wanted you to make sure you know how a full adder works. So you have an AN, BN, they go to an AND gate, XOR A, XOR B, XOR C. And then these are the logical output combinations. Some is A, XOR B, XOR CN. C out is A, XOR B, and CN or AV. And so I want you, in your lab, of course, to have the drawing and your logical calculations. Now, the reason why I'm having you do this, I know it's kind of fundamental, is because you're going to be taking a lot of this logic and applying it to other types of full adders. So you have full adder, and then you're going to be using carry look ahead, carry select, and ripple carry, carry select, and carry look ahead. We're going to discuss all 3 of these today. So here we have a Verilog description of what we've just talked about. So here we have A XOR B XOR C, and here this is a different representation of this logic. It's A and B, or B and C, or A and C, which is logic equivalent. So you could do B and C, or A and B. That Verilog code works as well. So this is what the full adder looks like when you're actually doing in CMOS. Let me zoom in a little more. Okay, so here we have our actual, we've inverted A and A bar, B and, this is a dual rail full adder. Okay, I should add dual rail. So dual rail allows for power consistency. We talked about how that's a security issue. So you have A and A bar, B and B bar, C and C bar. And from there, you can actually calculate sum. So this sum, and this is the carry out circuit using the dual rail adder. And then here we actually have the physical layout. So now again, if we were doing polygon-based extraction, we'd be checking we have our metals, we have our polys running here to here, right? And here we have metal when we have our pins. We're connecting through here. A and B or C, right? So you can see how all of this kind of connects together. your path, correct, so either VDD to ground, and eventually what we're trying to do is we're trying to get to an output. Here we have C out and sub. And so by having a different metal, so there's different metal types, those are now, as we now know, are on different layers within the metal in the SMOS DRC for your different hierarchies. So this here, this hopefully should explain why shorting it to ground is problematic. So if you had A or B, and let's say you accidentally did something like this. You have B, and here, instead of, let's say you left this one out, right? So that would also here. And so what you've done instead is you've extended a little further. So this pin, and you have another pin over here, shorts, right? So you fix this one over here. You flatten it before you do your DRC check. Then it passes DRC, but it doesn't logically work. So now you're like, well, what am I going to do? This is all kind of together and it's all flat. So you kind of, somebody points out in the lab after being surveyed for a half hour, you see, oh, hey, I think this is tied to ground. You check, this is tied to VDD. So you check this, check the outputs, DRC passes, woohoo, DRC. Okay, now run it again, different set of logical outputs. Crap, that wasn't the right answer. So if you're not, so this is where simulate and tweak is a real problem. So that's why, I know I've been jumping up and down and saying it a lot this semester, but hopefully this diagram is very representative of why that's important. So let me go back up here. So that's just the TGO. So these are brief examples of adder types. We're going to finish up with a Cogestone adder, and then we're going to conclude lecture. So first, ripple carry is what you know. Generate the carry bits in the next adder, and so forth. So a 32-bit ripple carry adder, like you'd be using in MIPS, just does it like that. It's a big O of, so here, N, right? So here, we're going to be cutting it in half. Here we do 16 bits ripple carry, and then a carry out. Here, what we're going to do is at the same time we're calculating if the carry in was 0, as well as if carry in is 1, and then we have two 16-bit results, and then we use the carry out from the first ripple carry adder as the multiplexer signal, and then we output the 16 through 31. So that cuts the calculation time in half, but it multiplies our area by 3/2. But as you can see, by breaking it down further and further, we can significantly improve our time, but the trade-off is in area and subsequently power consumption. So actually, we'll end here, and we'll start next lecture talking about the Cogestone adder. This is good progress. So the comparisons of ripple carry, carry select, and carry look ahead, as I've just discussed, has a slower execution time of big O of n. That means it takes n calculations to complete, but has a smaller space capacity of big O and n, means that we have n full adders. Has an improved execution time, so square root of n, but has slightly larger space complexity, which is big O of 3/2 n. And then carry look ahead has the best execution time, so it's big O of log of n, so it's just like the logarithm of the number. However, we're going to discuss this at the beginning of next lecture, it has a significantly higher space complexity. So we're going to talk about propagate, generate, and kill signals, and how you can use that to predict what the carry signal is going to be before you actually would calculate it. So you will only calculate it every full adder, but you can predict it using propagate, generate, and kill. And the most efficient method that we're going to start lecture next time is known as the Cogestone adder. And we're going to discuss that in class. Okay. So does anybody have any questions about what we've covered today? All right. So lab is still due Thursday. Make a mental note of everybody who showed up today. I might Well, is anybody's lab partner not here?